Okay, chapter 8, concepts only. We're going to be talking about potential energy and the conservation of energy. And in the next video, we will apply these concepts and work problems. The big ideas here are that there are two kinds of forces. We have conservative forces and non-conservative forces. Another idea is that potential energy is just a way that energy is stored, and mechanical energy is going to be the sum of your potential and your kinetic energies within an entire system. So let's start here with the differences between conservative and non-conservative forces. This is a general breakdown, and then we'll get a little bit more specific. So for a conservative force, the work it does is stored in the form of energy that can be released later as kinetic energy. I know that doesn't make a lot of sense right now, but let's think of an example. If there is a box sitting on the ground and I lift that box up, we know from the previous unit that the work is equal to m times g times h, the mass times the gravity times the height that we've lifted it. When we drop it, gravity is going to do the same amount of work to return it to the floor. That means our energy has been conserved. And that's why gravity is an example of this. Another thing to make note of is that with conservative forces, the work done moving an object around a closed path is zero, regardless of the actual path taken. As long as it's a closed path, the work done will be zero. On the other hand, we have non-conservative forces, which are forces involving a loss of kinetic energy that we can't get back later. So we don't lose it permanently. It's simply converted to some other form of energy, like thermal energy. A good example of this is friction. If we are pushing a box across the ground, it is not going to come back to its original position. Friction will prevent it from doing so. And then finally, the last point to consider is the difference here. With a non-conservative force, the work done moving an object around a closed path is not zero. It will not be zero. It'll either be a positive or a negative number. Okay, a closer look by what is meant with work done by gravity on a closed path is zero. So here we see our closed path, and in this case, it is a rectangular loop. Here, gravity is not doing any work on these horizontal segments. It is doing work in the vertical segments. However, that work is equal in magnitude but opposite in direction, so it cancels each other out. So the work done on the horizontal portions is zero, and then on the vertical portions from A to D and from C to B, we see that it's equal yet opposite. So they will cancel each other out, resulting in a net work of zero. In the previous slide, so here, we have a nice rectangular pathway. But with a conservative force, it doesn't matter what that pathway looks like. It is independent of the path. So the work is still going to be zero, even if we're making loops and turns and going around curves. As long as it is a closed path, it doesn't matter what that actual path looks like. The total work will be zero. And with a non-conservative force, so here we're not picking something up, we're sliding an object around on the floor. And yes, we're still sliding it around in a loop, but the work done by friction here on this closed path is not going to be zero. Why? Well, that's because each section has this component of friction, that coefficient of friction. So we're going to be moving it, and we are going to have a component of friction around each portion of this. Notice they're all negative, so we don't have equal yet opposite magnitudes here. They're all going to add up. So here we're going to end up with a work that's -4 multiplied by that kinetic friction coefficient times mass times gravity times distance. So these would add up to -4 instead of canceling out nicely like they did with the conservative forces. So gravity is a conservative force. The work done by gravity is conservative. The work done by friction is not conservative. And that brings us to potential energy. And I meant to take this term gravitational out, so you can just ignore the term gravitational. Look, I'm going to scratch it out. We don't need this. Ignore this term. This is just a general definition of potential energy. So we're going to use another example where we're picking something up. So we pick up a ball, we put it on the shelf. When we do this, we have done some amount of work on the ball. We can actually get that energy back if the ball falls back to the ground. But in the meantime, we're going to say that that energy from the work we did in the first place to get it to the shelf is being stored, and that stored energy is what we call potential energy. Something to make note of is that work is scalar. It is scalar, and its units are joules. So we represent work with a C, and this is conservative work. U is what we are using for potential energy. So not PE, it's U. U means potential energy. And this is the change in potential energy, not our actual values. We're looking at the change. That's what we care about. When we look at the change, we're actually free to choose where we want our potential energy to equal 0. So that's going to help us when we start doing calculations. And we can choose that similar to how we can choose the direction of our coordinate system. We don't need this part anymore. Okay. When we are talking about gravitational potential energy, please make a note that this is always near the Earth's surface. If we're talking about something out in outer space, this is going to change. So near Earth's surface, our change in potential energy, which is the initial minus final, that's why we have a negative over here, is equal to the work, which is equal to our mass times the gravity times y, which is our height. Traditionally, and the book goes into a more thorough explanation of this, not traditionally, this is how it is. The book goes into a better explanation of this, but normally we would say that UI, so our potential energy, is equal to mgy plus our final potential energy. But when we choose our starting point, or when we choose our final point, this one, where we choose it to where the potential energy is equal to 0. So we want to choose a spot where this makes sense. So here, they chose U to equal 0 at the level of the water. That makes sense. When we do this, then this term becomes 0. We can cancel it out, and we're just left with U equals mgy. So that's how we make this correlation. We can also look at this in terms of springs. So this is true with conservative forces only. And when a string is stretched from its equilibrium position, which we know to be this, where work is equal to 1/2 kx squared, if we actually let it return to its equilibrium position, it's going to do the same amount of work going back. And when we set our system so that the final potential energy is 0, again, just like in the previous problem, this will disappear, and we can say U is equal to 1/2 kx squared. And these are all equations you should be writing down. moving right along to the conservation of mechanical energy. So mechanical energy, which is represented by an E, is just the sum of our potential and our kinetic energies within a system. So potential plus kinetic energies. And when conservative forces are involved, our final and initial energies are going to be the same. So we can just say that E is constant because its value does not change. Even if non-conservative forces are involved for where mechanical energy is maybe converted to thermal energy, when we consider all forms of energy, we will still see that the energy is conserved. Now, because we can say that our final mechanical energy is equal to our initial mechanical energy, this is going to allow us to solve for speed, and we will get into this in the application video. I just wanted to mention it right now. So energy conservation can also be used to solve problems with springs, as well as problems involving changes in elevation. And these are problems that we can't solve with other methods. Now, how is that possible? Okay, so we would write our expression for the initial mechanical energy. And we see that right here. So our initial mechanical energy is equal to our potential plus our kinetic energies initially. When we plug in the appropriate information, we'll find that this becomes 1/2 k times d squared minus mgd plus 0. This 0 is for the kinetic energy, and that's because this is not moving right now. Before, it is not moving, so we can say that kinetic energy is 0 and cancel out that term. So this part is all for the potential energy, that from the spring and then whatever is happening with gravity. Second thing, we're going to write the expression for the final mechanical energy. And we see that here. Okay, so once it's moved, our potential energy goes to 0. And now we have our kinetic energy, which is 1/2 mv squared. We can set these equations equal to each other, set E initial and E final equal to each other because of what we previously talked about in the slide before this. And then all we have to do is solve for the final velocity, and then we would just put in our actual numbers and get a result. And again, we will do that in the next video. When the work is done by non-conservative forces, on the other hand, our mechanical energy is not conserved. So we see that our total work with non-conservative forces is going to be the sum of the work done by the conservative forces plus that done by the non-conservative forces. We plug in what we know because we know that the conserved work is just the potential and the kinetic energies combined. It's the sum of those. And we can find that our non-conservative work is the change in our potential energy plus the change in our kinetic energy, and that is equal to a change in the mechanical energy. So it's not going to be conserved, and we cannot say that E final equals E initial when we're dealing with non-conservative forces. Here is an example, and we're actually going to work this problem in the next video. I just wanted to show you what I mean by non-conservative forces. So let's say I have a glove and it's up here. And normally, if I've picked it up off the ground and then dropped it and it lands right here, that would be conservative because I'm picking it up and then it's returning back down with the same amount of work. But in this case, the glove actually falls into the snow. So it has gone farther down a greater distance than the height that I picked it up to. So that's what I mean by a non-conservative force. It would be H plus D. That would be my total distance that the glove has traveled, whereas I only moved it to the height of h. We can also look at potential energy on a curve. And the curve of a hill or a roller coaster is really just us plotting that GPE, that gravitational potential energy. Some things to make note of on these curves. At A and at D, our speed is 0. Those are turning points. And it's going to be moving fastest at B. Why? Well, that's because that's our largest or steepest hill. And so this track's shape will actually tell us the mechanical energy, because through this we can find U, so the potential energy, which is just the curve's height, plus K, the potential energy, which is the distance from the curve to the total height of the track. So I've labeled it over here for you. Well, the book has labeled it over here for you. U is the curve, the height of the curve. So U, and K is this other part, the part from the curve to the highest point in the track. And K, potential energy, would disappear at A and D because these are turning points where the ball stops moving for a split second. Potential energy curves for a spring are a little bit easier because we don't have this pathway. We have something that's more parabolic and easier to look at. So at our turning points here, that's where we pull the spring out and then it returns back to its original position. At these particular turning points where it's oscillating back and forth like this, y'all know what I'm talking about when a spring is moving back and forth. At the turning points, we know that the energy, the mechanical energy, is 1/2 Ka squared, or D squared. We're just saying A is our distance at this point in this particular example. Okay, so the string, we stretch it, and then it starts oscillating, and then it will eventually come back to rest again. And it's going to oscillate between negative A and positive A until returning to rest. But at these points, at these turning points, E is equal to 1/2 Ka squared. And finally, we have another way of looking at potential energy curves, and these are called contour maps, and you've likely seen one of these. So the different altitudes here listed in this map correspond really to different values for our potential energy, because we're at different heights and we know potential energy is mgh or mgy. So any line that's corresponding to a constant value for potential energy is something that we call an equipotential. And we're not going to talk a lot about those, but if you want to know more about them, they are in the book. That is it for our concepts. Here is a quick summary of what we talked about. I will just kind of let you read through these on your own. You can come back here and read through them. These are your key takeaways. And I will be back next time. We will work some problems involving potential energy and the conservation of energy. Thank y'all for watching.